Okay, so I'm recording the session for those who are not able to join us today. And shout out kay Hazel and Joanna for coming in today. Okay, so let's begin. So first off, start muna tayo on why we study solutions in the first place. No, okay. So let me just okay. So from the previous modules, no, we always assumed na yung lahat ng species involved are assumed to be I don't know pure substances, and when they are pure substances, then we can assume their activity to be equal to one. No, okay. So pero in reality, when we are dealing with real world na mga solutions, no, hindi all the time pure yung mga substances involved. So for example, in the industry, you can only produce as high as 6 nines only, no? Ito. I'm not sure if meron ng mga ano, no? Meron ng newer technologies that can go higher than 6 nines, pero in industry ito yung parang standard na standard purity na hinahabol natin. So 6 nines, it could be, for example, gold. If you want to refine gold, you want to refine steel, usually 6 nines yung industry standard natin. Okay? Now, this might be insignificant also. You might think na parang insignificant naman siguro yung 0.0001% na yun. But in some cases, yung 001 na yun could introduce several na parang changes to the properties of whatever species that is involved. No? So in fact, yeah, we can look into steel alone. No? So if you look at steel, steel is steel is just a alloy of iron and carbon. No? And yung percentage ng carbon, so if you look at something like eutectoid composition, no, it's only 0.8%. Pero yung 0.8% na yon, sobrang laki ng effect niya doon sa hardness ng steel. In fact, sobrang iba, sobrang hindi mo mako-compare yung hardness ng pure steel versus yung pure iron, I should say. Yung pure iron versus steel that is alloyed with just 0.8% carbon. Okay? So that just tells you how large the effect is kahit minute compositions lang. And we can look into other systems pa, no? For example, um, so for example, sa steels, let's go to steels again. No? So sa steel, if you have an impurity of, I forgot the exact number, no, pero just a small impurity of sulfur, that sulfur can cause what we call as, I don't know, short, wait lang, short hotness ba yun or hot shortness? Wait lang. I'm trying to remember the term. No? Pero anyway, I can probably remember it. It's either short hotness or hot shortness. Parati ko nalilito sa two terms na yun. Pero one is correct and the other one is wrong. Pero in any case, just a small amount of sulfur will will definitely make your material brittle. No? So parang instead of steel being so strong, parang ang nangyayari is si steel becomes brittle. And that's why in most refining industries, no, especially for steel, parang sobrang binabantayan yung sulfur levels. Okay? So therefore it is necessary na kailangan natin i-take into account yung parang minute changes na to, no? And this is where solutions come into play, no? So solutions are just a combination of two or more components, no, that are physically combined so as to form a homogeneous mixture. No? So yung keyword dito again is homogeneous. No? So it must be such that yung yung ano natin, yung material natin exists in only one phase. No? So for example, if it's a solid solution, then solid phase lang sila lahat. Tapos homogeneous siya in such, or hindi pala phase yung proper term, no? Mas maganda yung term na state of matter. So for example, if it's a solid solution, then it's a kumbaga isa lang yung nakikita nating parang mixture. So it's homogeneous. But if it's a heterogeneous mixture, which is the opposite of homogeneous mixture, no? Heterogeneous, kaya mo ma-distinguish or may boundary ka between the different mixtures. So a good example of heterogeneous mixture is, for example, yung, I don't know, perlite natin, no? So hopefully you still remember perlite. So kung perlite, if you look at perlite, kung isa to sa grain ng perlite, isang grain to, no? Perlite is meron tayong lamellar na Fe3C, no? Tama? So this is alpha plus Fe3C. Okay? So this is considered as a mixture because clearly delineated yung phase between the alpha phase and the Fe3C phase. But if you have something like alpha, ito yung grain natin, tapos may alpha ka dyan, tapos meron siyang dissolved carbon. So in the alpha can, let me double check. If I remember my phase diagram correctly, kaya ng alpha hanggang 0.02, no? Kasi dun sa left side ng phase diagram, ito siya, si alpha. This is alpha plus Fe3C. This is gamma plus alpha. Tapos yung ganyan siya. Gamma plus Fe3C. Tama? So, ito hindi ko na alam yung nandito. Medyo blur na yan sa akin. Pero definitely alam ko itong part na to, itong lower left. No? So, ang alam ko, this is 0.02. Okay? So, meaning alpha can hold a maximum of 0.02% carbon. Okay? So, pagka ganyan, this is one phase. This is homogeneous, no? This is homogeneous because the carbon is indistinguishable yung parang individual particles na because it is fully dissolved in your alpha. Tapos, pag mixture naman siya, so, take note that the solution is still a mixture, no? Pero homogeneous mixture siya. Tapos, pag heterogeneous mixture, yun yung nadidistinguish natin. So in this case, itong mga lamellar structure na to, ito yung Fe3C, tapos yung alpha yung parang host metal niya. Okay? So in chemistry, usually pag sinabi mong heterogeneous mixture lang yung term na ginagamit natin. So it's just simply term mixture, tapos pagka homogeneous na siya, solution na yung tawag natin sa kanya. Okay? Para hindi siya maging confusing nyo. Okay, so that is a solution. So it should exhibit the same physical and chemical properties throughout the homogeneous mixture. No? So for example, if kasi isa lang yung nakikita natin na physical phase, so we should expect na itong ano na to, solid phase na to should have the same properties whether we measure that property from here or if we can do that not using a nano indentor kunwari kung nag-hardness tayo. So if you try to measure this property versus this property, it should be the same, no? Kasi homogeneous siya. Which is different from, say, a heterogeneous mixture wherein kung dito ka nag-measure along the itong Fe3C phase versus uh, dito sa host alpha natin na phase, magkaiba yung ma-measure nyo na mechanical or physical properties dyan. Okay? So that is solutions. So in solutions, usually binary solutions yung pinaka-common, no? Kasi madali siyang i-imagine. Pero we can extend these definitions even to multi-component systems. No? So pagka sinabing binary, it's a two-component system and we can classify the components as either a solvent and a solute. Okay? Pagka sinabing solvent, siya yung component that is present in greater amount. Sometimes tinatawag din natin to as the host atom, no, or host material. Tapos yung si solute naman, siya yung present in the minor concentration. Minsan tinatawag din siyang impurity because it causes the solvent to be impure. No? So instead of 100% solvent ka, magiging 99 point something. So minsan tinatawag siyang impurity, no? Pero although the impurity carries a parang negative connotation, we learn from material science that impurities can actually have beneficial effects. No? For example, yung steel, yung impurity na carbon actually promotes or increases the hardness of your otherwise soft na iron. Okay? So that's solvent and solute. And minsan pagka kunwari marami kang component, solute lang din tawag natin doon sa mga other impurities that that contribute to your entire solution. No? Basta as long as it is present in minute amounts. No? So yung siguro may mga questions about paano sir pagka kunwari hindi malinaw kung sino yung solute at solvent. Something like kunwari 50-50. So, masasabi ba natin na solvent yung isa at solute yung isa? So, ito yung mga medyo vague na area, no, sa chemistry. In metallurgy, ang tawag natin sa mga systems na to na wherein hindi masyadong malinaw yung kumbaga hindi natin masasabi na alloying element. In terms of metal, no, tawag natin sa mga solutes is alloying element. Tapos ito yung host natin. If we talk about alloys, tapos yung combination of the host and the alloying element or minsan the base metal. So if you have a base metal, tapos inalloy mo siya with an alloying element, we call that as the alloy, no? And this is for metals, no? Tapos once you have something that looks like this, or kunwari 33, 33, 33, yung mga ganitong klaseng compositions, ang tawag natin dito is, although hindi na siya importante sa ano, no, pero something to siguro baka maging interested kayo dito in the future, no? Ang tawag natin dito is high entropy alloys, no? And high entropy alloys are actually a good field of research, no? So if you want to go into kunwari, studying physical metallurgy, isa to sa mga pwede niyong pag-aralan, no? Si high entropy alloys. Very interesting yung field na to. In any case, pero dito naman sa MetE17, we will always present mga systems that have clearly defined kung alin yung solvent at alin yung solute. So something like mga 99:1, mga ganyan yung mga composition na ibibigay namin sa inyo. Okay? So yung ideal solutions natin, these are solutions that obey the Rayleigh law, no? So and this is across all temperatures, applicable temperatures and pressures, no? And ang Rayleigh law is defined as this simple equation right here, no? Wherein sinasabi niya na yung activity ng isang component, let's say component I, is just equal to the molar fraction of that component I. Okay? So parang linear yung magiging ano niya. So you can notice here na, for example, this is a graph showing the this is increasing component B, no? So in this section right here, we have 100% component A. Tapos dito, 100% component B. Okay, so if you look at something like here, that's 25% component B. Tapos dito naman, mga 75%. Okay, that's dito, 50%. So this is in terms of component B, no? So dito, 0% component B, you'll notice na yung activity ni A will be equal to 1 because the molar fraction of A, dahil 100% A nga to, is equal to just 1, no? So meaning yung activity niya will be equal to 1. Now as the contribution of B increases, so for example from here, slowly tumataas yung parang concentration ni B, you'll notice na magde-decline yung activity ni A. And at the same time, nag-i-increase din yung activity ni B. Parang ganyan. And this happens if you are an ideal solution, or this happens in a linear manner. So as you grow in concentration, naabot ka sa point na magiging 100% si B. So kung 100% naman si B, magkakaroon tayo ng activity of B just equal to 1. Okay, tapos the activity of A is equal to 0 because A is non-existent once we have 100% component B. So very straightforward lang yung equation natin, no? It's just the activity will just be equal to the molar fraction. So the greater the the molar fraction, the greater its activity will be. And activities are expressed from 0 to 1, no? Okay? Kasi ang molar fractions natin 0 to 1 lang din. Okay? All right. So let's try this example, no? Let me shift to my. Okay. So ito yung example natin. We have a basic hearth process. Tapos the reaction of manganese in the bath with iron oxide, FeO, in the slag attains a condition very closely approximating true equilibrium. Meaning yung amount of exchange is now equal, no, yung forward and backward reactions. So the steel contains around 0.065 atom percentage. So this is in atom percentage, no? And the slag analysis by weight is 81.09 FeO, 13.86 MnO, 3.74 MgO, 1.06 SiO2, and 2.25 CaO. Okay, so we are to calculate the equilibrium constant and standard free energies for the reaction at 1655 degrees Celsius. And we are to assume that the slag and Fe manganese system behave ideally. No? So let us neglect the effect of other metalloids present in the steam. Okay, so to imagine this, kailangan muna natin ano no, it's helpful if we imagine kung ano yung itsura nung bath na to, no? Tama? So let me pick a brush. Uh, ganito. So, okay. So, imagine muna natin yung brush natin. So, ay brush yung yung system natin, no? So we have our melt. So when we have a parang ganito process na ganito, no? Uh, Turn off ko lang to shape dynamics. Okay. Ayan, okay na yun. So for example, meron tayong ganito, no? Tapos, this is our container or our hearth process. So ito na yung bath natin. Tapos, meron tayong two layers, no? Two distinct layers. So dito sa baba, we have our Fe manganese. So, dito yung Fe plus manganese na bath natin. Okay? Okay? So meaning this is pure Fe with or no sorry. This is containing the solvent Fe tapos meron siyang solute na manganese. So this is the solvent. Tapos etong manganese natin, siya yung magiging solute natin. Okay? So above the Fe manganese bath will be our another layer, no? And this layer is our slag layer. Okay? Usually kasi the slag contains, I don't know, I hope you remember or sana na-cover to kahit papano sa ano no sa MetE11. So when we do extraction pa yung mga lalo na yung mga pyrometallurgical process no. Na dahil yung metals natin is has a very high affinity for oxygen. Usually nagpo-form siya ng mga oxides no. And yung oxides natin mapupunta sila lahat sa isang layer which is the slag layer. So kaya ang slag layer usually parang metallic, glassy yung finish niya no. So because it contains mostly mga oxides. And the slag layer exists on top of the melt because the slag is lighter no because it now contains it contains oxides, then those oxides are less dense than your pure metal. No? So mangyayari, yung slag layer natin will float above the melt. Okay? So this slag layer here will contain the itong mga oxides na to. So that's CMNO, MgO, SiO2, CaO. So slag lang oxides. It will contain the oxides. No? Okay? So, ang sinasabi niya na we are at equilibrium, this is saying na yung exchange between yung slag natin and so yung conversion kumbaga ng Fe to its oxides and Mn to its oxides will be parang equal na no yung forward reaction to become an oxide and yung reverse reaction to become a pure metal, parang yung rate nila is equal na no. Okay? So because that is one of the definitions of equilibrium no, meaning na it's not pushing one way or the other. Nasa if we draw the parang imaginary na energy curve na to, parang nasa lowest state na siya. So it's not pushing this way, it's not pushing that way. We are at equilibrium. Okay? So, pwede natin isulat yung mga equations na involved dito, no? So, we have yung chemical reaction natin na hindi ko pala nakopya. And I think we should also get the molecular weight. So, given naman. So, nandito siya. Okay? So, ito yung molecular weights as well as the equation, no? Okay? So, ang sinasabi dito is that this is the reaction. No? We have FeO um, plus Mn will yield MnO plus Fe. So, this is our main reaction. No? Okay? So, ang notation dito is that pagka ganito siya, yung parenthesis, it's in the slag. Pagka ano siya, a square brackets, it's in the melt. Okay? So, to be more accurate, no, this should be reversible reaction siya kasi we are at equilibrium. No? So, meaning, yung rate ng transform ni FeO into pure Fe is equal to the rate ng pag-transform ni Fe into FeO, and as well as si Mn into MnO and MnO into Mn. Okay? So, if this is the case, then we can just write the reaction quotient, no? If we write the reaction quotient, Q is equal to um, the activity of, let me, or Q is equal to the activity of the products, which is Fe, plus the activity of the, sorry, not plus, times the activity of MnO divided by the activity of FeO tapos yung activity ni Mn. Okay? So ito yung magiging working equation natin. So that's our reaction quotient, no? Tama ba? So pwede rin, since we are at equilibrium, KQ na lang sasabihin natin. Right? So now that we have this, then we can use the fact that because we already established na it behaves ideally, no? So pwede natin sabihin na yung activities na to equal lang sa molar fraction ng mga species na to. So we have Fe, molar fraction yan, molar fraction ni MnO, molar fraction ni FeO, and lastly, yung molar fraction ni Mn. Tama? So, to compute these molar fractions, pwede natin gamitin yung ano lang, no? Yung slag analysis, pati yung itong fraction ni manganese. Kasi 'di ba, sabi natin, this is one solution, so meaning one homogeneous mixture to, and this is another homogeneous mixture, no? So this is one solution and one solution. So para makuha yung molar fraction of the solution, then kailangan lang natin kunin yung weight ni manganese, kunwari weight manganese over weight, molar fraction pala to na. So moles ni manganese over number of moles ni Fe para makuha yung XMN. So similarly, ganun din gagawin natin sa Fe, no? Tama. And if we add the molar fractions, that should be equal to yung X total should obviously be equal to 1, no? Tama? So that's X total for the slag. For the melt should be equal to 1. Tapos yung X total din dito for the slag should also be equal to 1. Okay? Tapos, given naman yung mga molecular weights, no, so we can actually compute for them. Okay? So, we can have, to simplify our equation, no, although if you use a powerful calculator, parang hindi na necessary itong step na to. Pero, we can actually just simplify this, no, because if you look at this, parang the steel contains 0.065 atom percentage of manganese, which is very small, no? So, we can simplify itong XFE na to. We can say na this one should be equal. We can assume na equal to 1 lang siya, no? Because it's very XMN. And sulat ko lang dito. Yung XMN natin is very much smaller than yung XFE natin. Okay? So, we can just assume that to be equal to 1. So, we end up with XMNO over XFEO, Mn. Okay? So, ito na yung working equation natin um, for the K equilibrium. And from the equilibrium constant, pwede na natin makompute din yung standard free energy, no? Because we know that the standard free energy, delta G naught, is just equal to negative L RT ln K EQ. Tama? Okay, so let's compute for ito mo ng XMN. No? So XMN is, we know that Mn is equal to, naka-atoms na kasi ito. No? If you look at it, it's already in atom percentage, meaning number of moles na rin yun. Tama? So if it's 0.065 atom percentage, then that just means that XMN, and isulat ko lang dito, XMN is just equal to 0.065. Ano, sorry. 0.065%, so that's over 100 pa. Tama? So that gives us, kasi percentage, so that's 6.5 times 10 to the 1, 2. 1, 2, 1, 2, 3, 4. 10 to the negative 4. Tama, no? Just correct me if I'm wrong, guys. No? Okay. So, compute natin si, um, let's compute the no, sorry, the molar fractions of the different of the different species involved in the slag, which is XFEO and XMNO, no? So to compute that, kailangan natin si molar weights and si percentages, no? So it would be easier if we actually build and let me open Excel, baka feel ko mas madali. So bukas tayo ng Excel. Tapos kopyahin lang natin itong mga different na na to. So let me open Excel. Open ko lang. So that's, you have 81. Let's do weight percentage. Excel. Nakita niyo yung Excel ko?
Hindi po.
Ay, hindi pa. Ayan. Kita na, no?
Okay na po.
Okay, thank you. Si Joanna ba yun? Thank you, Joanna. Or si Hazel. Okay. So we have nandito. Before I proceed, no? Joanna asks, may cases ba na 50-50? Ayun, may cases. Ito, sinagot ko na pala ito kanina. So may cases na ganun, 50-50. And we call those as high entropy alloys. No? Okay? So, let's write all the weight percentages. No? So we have, or lagay ko muna yung species. Or, ano yun? Tapos weight percentage. Tapos, kunin natin yung magiging molar fraction. Molar fraction x sub I. Okay? So we have FeO. Tapos meron tayo MnO, NMgO, SiO2, and CaO. Okay? Tapos ang weight percentages nila is 81.09, 13.86, then we have 3.74, 1.06, and 0.25. Okay? Tapos Lagay lang ako ng isa pang ano, no, para mas madali. We can compute for yung molar weight, molecular weight niya, no, which is 71.85. That's grams per mole. MnO is 70.94. Nasa given naman to. And you can compute it using ano, no, periodic table naman. SiO2, no, sorry. CMgO is 40.32. SiO2 is 60.09. And CaO is 56.08. Okay. Now, this is gram per gram, no? And we want to compute for the molar fraction. Then what we do is kailangan natin makompute um, yung number of moles muna, no? Tama? So to get the number of moles, ang gagawin natin, let's just be sure na ano, 100 nga ba to? 100 naman siya. Okay? So to get the number of moles muna tayo. Moles, just multiply, wait lang, gram per mole. We divide the weight percentage by the molecular weight, no, to get the number of moles. Okay. And yung total number of moles, actually parang ano na rin siya, no, kasi if we assume 100 grams uh, of of this slag, then yung total will also be equal to 100 na. So parang eto na rin yung molar, ano, sorry, tama, mali. So para makuha yung molar fraction, divide pa natin to by 100. Okay? Lagyan natin ng F4 para ma-fix. Drag it down. And to be sure, dapat if we did this correctly, ang total nito is just equal to 1 dapat. Pero bakit hindi siya equal to 1? Kasi yung total number of moles. Mali pala, sorry guys. The total number of moles is sum nito. That's 1.43. Then we should divide it by, sorry. Scratch that, no? We should divide by the total number of moles para makuha yung molar fraction. Tama? And this is correct now, no? So this makes a lot of sense now. So ito yung molar fraction for FeO. Ito naman sa MnO, MgO, SiO2, and CaO. And if we add all of that, we should get the total, and this is for the slag, no, equal to dapat to 1. Okay? So tama na to. So we have these values. Tapos siguro, pwede ko ba hide ko lang to? Kasi huwag na natin hide. Copy lang natin diretso sa Photoshop natin. Okay? So, I'll just say na nag-Excel tayo. So now, ipa tayo sa ano. We can now compute for these two values, no? Itong XFEO pati yung XMNO. Okay? So, XFEO is equal to 0.784. Pwede ko pa na isulat na lang diretso, no? So, I'll just write it directly dito, no? So, XMNO is 0.13. So, that's 0.135. Pwede siguro 1358 divided by XFEO is 0.7844. Tapos XMN kanina, which is 6.5 times 10 to the negative 4. Okay? And let's calculate that. Saan natin yung calculator natin? Casio. Okay. Kita ba yung calculator?
Hindi po.
Oh, hindi kita. Wait, bakit hindi kita? Ayan. Kita na, no? Okay. So let's
Okay na po.
input. Thank you for the feedback. So that's 0.1358 divided by, that's 0.7844 multiplied by 6.5 times 10 to the negative 4, which gives us 266.35. 266.35. Ito yung KEQ na natin. Tapos, kailangan na lang natin is yung delta G, no? So, delta G is equal to, and copy na dito. Nilagay ko. Lagay natin dito. Dito na lang. So, delta G is equal to negative RTL and KEQ. So, this should be equal to negative 8.314. Gusto natin joules. Temperature is 1655. So, that's 1928 Kelvin. 28 Kelvin. Tapos, multiplied by ln of 266.35. Okay. And we should get, if we take the ln nito, tapos multiplied natin by negative 8.314 multiplied by 1928 gives us, ano yan? Hindi ko nakuha. Wait, sorry. Saan yung calculator? Nagsara ba yung calculator? Nawala yung calculator. Okay.
Nawala po.
Nakuha niyo ba yung sagot?
Negative 89520.99.
So, 89.20?
Negative 89520.
89520. Kaya sabihin natin 8.
0.99. Ano, bali 89,000 po kasi. Okay.
Kilojoules na lang natin.
Apo.
Okay, so 89.52 kilojoules. And this will be our final answer for delta G. No? Okay, so double check ko lang kung tama yung sagot. Nakakal pala yung sagot sa ano. But anyway, I think this is okay na siguro to. Sige, convert natin to calories para sure, no? So if you want to convert this to calories, multiply lang natin by 1 point, ano ulit yung conversion natin? Naalala ba? 96? Tama ba to? 8.314. 96 tama. Let me just double check last na kasi medyo limutan ko. Gas constant. Calories. 1.98 pala, sorry. 9872. 9872. So let's convert. So that's 89.52. Sorry. 8952 times 1.9872 divided by 8.314 gives us 21. 21,396. So 21.4. 21.4 kilocal. Okay. So almost the same naman. Okay. So yan yung makukuha natin if we assume ideal conditions. Okay. So before I proceed to we have 30 minutes left for ano, no, real solutions. But before I proceed to that, may questions ba about this, Hazel or Joanna?
Wala naman po sa akin.
Okay, wala naman si Hazel. How about you, Joanna?
Wala naman po, sir. Hinahanap ko lang po yung PowerPoint sa Oble. I-upload pa lang po ba siya or hindi ko lang po?
Ang alam ko, dapat na-upload na yun, pero baka hindi pa na unhide, no? Pero
Hmm,
definitely i-unhide namin siya tonight dapat.
okay po, sir. Thank you
Okay.
po.
Thank you for the reminder, Joanna, no? Okay. So yun, for ideal cases naman, madali lang siya, no? Ang siguro ang hirap, ang difficult part lang dito, class, no, is determining itong heart process na to, kasi baka not all of you can readily imagine kung na ganito siya, no? Tama? Yung delineation between the slag and the melt itself. So Fico, dito kayo malilito. Pero if this figure is given, tapos given din tong equation na to, I think you would find it easy na lang, no? Okay? So just remember na you can only, yung activities mo is based on which solution you are part of. Okay? So for example, notice how itong si MgO, SiO2, calcium oxide, wala silang effect dito sa melt natin, sa FeNMN. Tama? Wala silang effect specifically because hindi naman sila part ng melt na ano. So kumbaga wala silang influence doon sa parang activities of the binary components Fe and Mn. Pero itong SiO2, calcium and manganese oxide, or sorry, magnesium oxide, meron silang effect doon sa slag side naman. Notice na dito hindi lang nung kinumpute natin itong dalawa na to, no, itong when we computed for FeO and MnO na Xi, or yung molar fraction nila, kinonsider natin yung other components that are present in the slag, which affected their values, no? Kasi kung wala to, dapat mag-iiba yung total natin. So kunwari lang hindi natin kinonsider to, mag-iiba tong total, therefore mag-iiba din tong X sub I na to, itong molar fraction. Okay? So kailangan natin dahil nga nakaka-affect siya doon sa activities, kailangan natin sila i-consider. Okay? So yun. So that's for ideal solutions. Proceed naman tayo sa non-ideal solutions. So let me open. Okay. Yan. Okay. So these are non-ideal conditions. No? So we've noted that for ideal conditions, nagpo-follow siya ng linear na no, na parang linear trend when it comes to activities versus its molar fraction. And that is what we call as Rayleigh law. No? Pero when we now proceed to non-ideal conditions, meron siyang actually konting deviation. No? So if you notice, itong line na to na nasa taas, yun yung Rayleigh's law. Tapos, if you take any concentration, let's just say concentration dito na part, there is actually a difference. No? And this difference is what makes non-ideal solutions. No? Because kumbaga nakaka-affect yung because of how the solutions interact with one another, nagbabago yung parang activity niya, yung real activity niya, yung non-ideal activity niya doon sa solutions that it is a part of. Okay? We can take into account, kasi ang assumption kasi nung ideal solution is that yung interaction between tin SB is the same, or this is the interspecies interaction. So let's just consider this ano na to, itong graph na to. This is for tin and your antimony. So dito kasi sa ideal conditions kasi ina-assume niya na yung interspecies na interaction is exactly the same as your same species interaction. So for example, if you have tin dito and antimony, dito accurate, no? Hindi ko alam kung ano talaga sizes nila. Pero sige, para hindi ako well, let's just say ganito na siya, no? So itong circle is tin, ito yung antimony. So, ang assumption ng ideal is that regardless if si tin is surrounded by antimony or si tin is surrounded by tin, ang interactions nila is just the same. Yun yung assumption ni ideal conditions. Pero we find out that etong interaction na to is not the same. No? So for example, if you have a solute natin si antimony, mas marami yung tin na nakapalibot sa kanya. Kasi 'di ba, if you're a solute then you are present in minor amounts as compared to the host atom. So ibig sabihin, yung significantly lower yung magiging parang Sb to Sb interaction as opposed to yung tin to Sb interaction. Tapos significantly greater din ang tin to tin interaction kasi mas maraming tin to tin. Okay? So all of those differences will contribute to the non-ideality of our solutions. So if you look at a graph, ito yung graph natin kanina, no? This is the activity versus the percent composition. So this is where you have 100% A or 0% B, tas dito naman 100% B, no? So increasing si B in this direction. So you'll notice na in ideal conditions, di ba straight siya kanina, parang ganito. So if you have, for example, 0.5% B, then it is expected na 50% yung activity niya. Pero notice dito na meron siyang parang ano, no, deviation. And this deviation right here, ito, we call this as a negative deviation, no, because the graphs are pushed downwards, no? So it's lower than the expected na ideal condition. Okay? So ang net effect nito is such that kung mag-add ka ng B to A or A to B, maglo-lower yung activity for both components. So yun yung negative na deviation, no? And some systems that exhibit negative deviations are yung silicon Fe system natin tsaka yung lead tin na yung tin lead system. Okay? Now yung opposite naman sa negative deviation is what we call as a positive deviation, no? And if you look at 50% ulit, tingnan natin yung 15%. You expect it na activity B is at 50%, pero you'll notice na it is greater than 50%. Nandito siya. Okay? So, opposite to your negative deviation, ang net effect nitong positive deviation is that kung magdadagdag ka ng A to B or B to A, magre-result to ng increased activity in both of the components. So examples of positive deviations are manganese in iron, Fe in lead, and copper in iron. Okay? So because of this non-ideality, no, kailangan natin ng correction factor dun sa ideal case natin. Okay? So, 'di ba kanina we just equate, since it's a linear equation, no? Yung activity natin is just equal to the activity na to is just equal to this molar fraction. Now, for non-ideal conditions, magdadagdag tayo ng correction factor. And we call this correction factor as your thermodynamic activity coefficient, no? Ito siya. Or simply, minsan din tinatawag lang siyang activity coefficient, no? And this was introduced by si G. and Lewis, no? Okay? So, yung activity coefficient natin is closely related to the composition, and it is also dependent on the temperature and pressure. No? So, different conditions ng temperature and pressure, magbabago din yung activity coefficient na to. Okay? So, when we have a negative deviation, yung correction factor natin should be less than 1 because again, yung net effect niya is to lower the activity of the species of both the components involved, no? So kailangan it's a fraction, no? So it's less than 1. Pag ideal naman siya, then your activity coefficient or correction factor is just equal to 1. Tapos pag positive deviation naman, the activity should be greater than 1. Okay. Now, if we try to apply this activity for the Gibbs free energy, no, so we can state that the Gibbs free energy for a particular species can be equal to just RT ln ng activity of that particular species I. Tapos if we introduce gamma, then this will just become parang ganito lang, no? Kasi magiging RT ln gamma activity. So pag sineparate nyo yung dalawang to, magiging RT ln gamma I plus RT ln xi, no? And since for ideal solutions, ln gamma is just equal to 1, then this whole term becomes 0, no, for ideal solutions. Okay? So, a key observation na pwede nating makita for non-ideal conditions is that the activity coefficient changes with mole fraction. No? So, if we look at this graph right here, ito kasi yung deviation from rails, no? So, this is the ideal condition. Notice na hindi siya, kumbaga paiba-iba yung slope niya. Okay? So, if we have a constant na gamma, kunwari, yung gamma natin is just constant, no? At any mole fraction, then therefore, yung line natin should look like ganyan lang dapat. Tama? Kasi kung constant lang siya, if its activity is equal to a constant multiplied by the mole fraction, then yung line mo will just adjust its value, no? Pero linear pa rin siya. Okay? Pero hindi yan yung case, no? So if you look at it, um, if you say for example take this point, ang instantaneous slope niya dito, if you take the instantaneous slope nito, it's different from the slope dito. Tama? This is smaller, this has a smaller slope, this is a larger slope. So meaning yung activity coefficient is also a function of mole fraction, no? So as you change the mole fraction ng in this example, it's XA. So if you change the mole fraction of XA, nagbabago din yung parang correction factor gamma or activity coefficient gamma A, such that uh, hindi siya constant across all of the points dito sa ano na to, itong non-ideal curve na to. Okay? So if you look at this, if the XA approaches dito sa ano, as it approaches 100%, it actually behaves ideally, no? And we can also look at it dito sa previous graphs natin. So notice na pagka yung X sub A natin approaches 100%, parang nagme-merge actually yung ano natin, nagme-merge yung ideal line and non-ideal lines. And it's also applicable din dito, no? So this says that whenever you have your concentration approaches the 100% of concentration, so parang nagiging insignificant yung if we look back at the tin and SB na example, no? If kung sobrang dami na ng tin mo as opposed to antimony, ang mangyayari is sobrang insignificant na yung contribution nitong tin SB as opposed to the contribution of the tin-tin interaction. So parang nangyayari is it's as if nagbe-behave itong solution na to, itong tin antimony solution na to as if 100% tin na lang siya. So parang dahil insignificant na nga, para siyang kumbaga sorry, not 100% but it behaves ideally na. Okay? So this means that so yun yung first observation natin, no? As it approaches 100% contribution, ang nangyayari is nagiging more ideal yung solution natin. Pero one interesting na observation is that pagka nag-approach siya ng infinite dilution, meaning if this is X sub A, no? And our component, our host is B, kunwari yung solvent natin. So we have solvent B. Tapos solute natin is si A. Okay? So infinite dilution means that solute is the solute composition XA is approaching 0. So yun yung ibig sabihin ng infinite dilution. No? So at infinite dilution, ang nangyayari is hindi actually siya lumalapit sa ano no, hindi siya lumalapit sa dito sa ideal condition na behavior. Ang nangyayari is lumalapit siya sa itong isang line na to no. And we call this as Henry's law line. Okay? So this the slope of this Henry's law line is your gamma A that hindi ko alam kung paano siya sinasabi no. Pero let's just say gamma A naught siya. Pero ito siya, this is a unique na ano no number that is a constant for specific na solutes in specific solvents. Okay? So as you approach infinite dilution, ina-approach mo tong constant gamma na to. Right? And this is useful because it's useful kasi itong in most systems naman, lalo na pag inaaral natin uh, yung mga solutes most relevant na mga solutions no that studies solute and solvent na interaction, they are done at very minute na compositions no. And therefore it's important to know na kung ano yung magiging behavior niya at those infinite dilutions no. So itong ina-approach niya, 'di ba it approaches the Henry's law. We call that as ano no, yung Henryan behavior. So when a substance or a solute approaches infinite dilution, it approaches what we call as Henryan behavior. And yung Henryan activity we'll discuss more about it no sa next na lesson natin, which is next week. Tapos magko-compute tayo ng mga Henryan activities as opposed to just the normal thermodynamic activity no. And Henryan activities are given the symbol H. So whenever you see H, ibig sabihin nun Henryan activity. And we had a preview about this no, itong Henryan activity dun sa if you've read the module about um thermodynamics of surfaces, you should be able to see na meron doon topic na or may equation doon that yung excess free energy gumamit siya ng HB no. Parang yung may isang equation doon, yung excess free energy, HB yung ginamit. So HB means na it is Henryan activity as opposed to just thermodynamic activity. Okay? So yun. Let's try this example. Meron daw tayong ano no? Open ko na rin yung di pa tayo sa Photoshop natin. Alright. Okay. So ito yung ano natin. I-expand ko lang yung working area ko. So let's consider the dilution of N2 gas in molten Fe. And the N2 gas can dissolve in small amounts into the liquid Fe when it sits on top of the melt at high enough pressure. So what would be the expected concentration level of N if the partial pressure of the N2 gas can be adjusted? No? So this is useful. Usually nagagamit natin itong ano, no, pag-dissolve ng N2 gas into the Fe melt if you want to produce yung parang ano no, medyo hard na type of yung alloyed steel na medyo matigas no kasi formation of nitrides actually produces very hard na um, metalloids no or what do you call that? Uh, Nakalimutan ko. Nitride is a form of parang ceramic siya no. So ang nangyayari is nagpo-form siya ng um, parang matigas na na precipitates that contribute to the hardness of the bulk material no. So itong N2 gas ano pero in most cases usually hindi Fe melt yung ano no parang pinupurge mo lang at high temperature sa isang kunwari buo na siya na metal no. Usually ang mas relevant na scenario is meron kang Fe alloy. Let's just call this a steel, no? May steel ka dyan, tapos ipapurge mo yung nitrogen gas at high temperatures. As ang nangyayari is nagdi-diffuse yung nitrogen sa labas, and it reacts with your Fe to form nitrides, and those nitrides form a hard layer outside. No? Ang tawag dito is case hardening. So, although hindi na siya masyado importante dito, pero parang ganyan siya. Pero in this case, this is not case hardening. This is more of parang gusto natin i-dissolve si N2 gas sa loob mismo ng bulk material natin. Okay? So, ito yung magiging itsura niya, no? So, we have your Fe melt. This is one solution. Tapos, in that solution, it contains dissolved N, no? And dissolved N here is, kumbaga, um, isang species to sa, technically, parang by component na to. Tama? Binary solution to in a way. Kasi ang meron dito is, you have your XN, tapos you have your XFE. And yung total ng sa melt na to, the total of the melt should be equal to 1. No? Tapos doon naman sa taas, it's just a one mixture or a gas solution lang siya, which is just N2. No? Wala naman siyang other gases involved. Okay? So when you are in equilibrium, same sa doon sa example natin kanina of the slag, we are saying that the amount of gas that is dissolving into the melt and is being released into the gas is equal. No? So the rate that it is dissolving equal lang sa rate that it is being released into the gas sitting atop of it. Okay? So ang magiging relevant equation natin dito will be yung N2 gas natin. Let me write it here. So we have N2 gas is equal to 2 times N that is dissolved. No? Okay? So we are saying na, and this is 2N because once na, this is a diatomic gas, no? N2 is diatomic, pero once that it dissolves into the Fe, it exists as parang N atoms na siya floating around or dissolved inside the host Fe. Okay? So magiging N2 is just equal to, or N2 produces 2N and reversible yung reaction kasi we are at equilibrium. No? Okay? So if we were to compute the equilibrium constant, KEQ now becomes products, which is the activity of N raised to the power of 2, no? Kasi 2N siya. And this is equal to activity of N2. Tama? Now, yung activity, we compute for the no? So ito, the activity of your nitrogen dissolved will be equal to, and we are not assuming ideal conditions dito, no? So we assume na, or we are not assuming ideal conditions, so therefore, we are noting na non-ideal yung behavior na. So if it's non-ideal, then its activity should be equal to the thermodynamic activity coefficient alpha n, and more specifically, this should be n in Fe, no? Kasi magkaiba yung activity coefficients nila pagka magkaiba din yung parang host atom. Okay? So to be specific, we say na this is N in Fe. Okay? So that's X N in Fe multiplied by the molar fraction of N. Okay? Now we divide that by, since this is a gas, then the activities of gases from the previous lecture, no, we noted that it is measured in terms of partial pressures. Okay. So rearranging this, we have we can get, paano ba to? Kung i-rearrange natin to, wait, this should be squared, no? Tama? Tama, squared. May squared pa pala. If we try to rearrange this, we should get xn is equal to, so lipat natin, this is KEQ over gamma, lagay ko lang gamma n, no? Gamma n squared multiplied by partial pressure of N2. Tama? And this is also squared. So if you get the square root, then you should get x sub n is equal to square root ng KEQ times the partial pressure of N2 divided by the coefficient sigma n. Now, ito, these are just all constant, no? Kasi itong K equilibrium is a constant, gamma is also a constant, then we can just replace this with just one constant, no? Let's just call it K prime. Minsan, kasi K prime lang. So that's Pn2 xn. So ito yung magiging equation natin, no? So this is how the molar fraction of any dissolved of the dissolved n, this is the molar fraction of the dissolved n is equal to or is directly proportional to the partial pressure of the gas above it. And this is no, I think you remember this equation. Oh, sorry, this should have a square root. Feel ko na daanan niyo to sa chem subjects, no? In Chem 16, 17 namin tinuro to eh. And maybe you remember this name. This is actually Shievert's law, no? Okay? So, ito lang ba yung hiningi na problem? So, tama no? What would be the expected concentration level of N if the partial pressure of N2 gas can be adjusted? Okay? So, parang sinasabi na if you adjust the partial pressure, it's directly proportional to Xn by this equation, no? So, square root siya ng partial pressure. So, if you increase the partial pressure, for example, 10 atmospheres, then that's yung magiging Xn mo will be square root of 10 times yung whatever constant na to. And this is Shievert's law, no? And Shievert's law is all applicable to diatomic gases, no? So when you have a diatomic gas, uh, and this is how Shievert's law is stated, no? Whenever you have a diatomic gas, the dissolved metal is proportional to the square root of the partial gas hovering above it. Okay, and this is exactly the case. No, meron kang dissolved metal, and there is a gas hovering above that dissolved metal. Okay. Yeah. So let's look at other examples. No, so ito meron tayong isang example pa dito. But here, I think we need Excel para dito. No? And we could probably do this as our last activity. No? So we have the activities of aluminum at different concentrations in AlCu solutions at 1,100 degrees Celsius or 1370 Kelvin are given below. So ito siya. This is molar fraction. This is activity. Then we are to calculate the activity coefficient of aluminum in a solution containing 49 atom percentage of aluminum. Okay, so that's just saying 49 atom percentage, just 0.49 molar fraction lang din. So to compute this, kailangan lang natin gawin is actually ipa-plot lang natin to. No? So if we take Excel, hindi pa tayo sa Excel. So the way we approach this problem is, okay, kita naman no, yung Excel ko. Let's do a new sheet. Let me just type quickly. No, 1.9, 0.75, 0.63, 0.53, 0.45, 0.3, 0.2, 0.1. Tapos 0.89, 0.69, 0.5. Tell me if I'm typing correctly. 0.2, 0.1, 0.03, 0.005, 0.008. Okay. So this is my X aluminum. This is a molar fraction aluminum. Kasi ito, activity aluminum. Okay. Gagawin natin, ipa-plot lang natin, no? So, kailangan kasi natin is mag-plot tayo ng, kung baga gusto natin malaman yung deviation niya, no? We can do activities sa y-axis, tapos yung, and let's do molar fraction sa x-axis. Okay? Pero Fico, it doesn't really matter, no? Kasi uh, x is equal to, or sorry, activity is equal to gamma times x, no? Tama? So, parang mas madali ata if y-axis si activity para y is equal to parang kx. Tama lang? Makes much more sense. So, compare natin to. And feel ko mas madali if we palitan natin yung table, no? Wait. Gagawin natin siyang transpose natin ng ganyan. So, it's much easier to work with. Okay, so let's insert a chart. Ito, insert tayo ng chart. Scatter plot na ganyan. Okay? So, this scatter plot is, ito yung activity niya on the y-axis versus the molar fraction niya. So, if we want to get the activity, then there are many ways to do this, no? So, ang kailangan lang kasi natin is yung 0.49. Kunin natin yung slope at 0.49. Tama? So, you can do, this now depends on what technique you'll use, no? So, pwede kayong, you can do derivatives. So, if you try to, kaya ba natin mag-add ng trend line? Polynomial siguro to. Power. Exponential. Walang masyadong nag-fit, no? So, medyo mahirap siya. Medyo pangit yung graph. Power, hindi rin logarithmic. So, medyo mahirap no? Kasi, di ba, if you remember your math, pwede kasing gawin natin is, if we take the derivative of a function, yun actually yung, yun yung parang slope at the different points. No? So, for example, kung kukunin natin yung derivative nito, tapos meron tayong equation na nakuha, input natin yung 0.49 doon sa derivative. So, f prime of 49, 0.49. That should give us the gamma, no? Or kaya natin ma-extract si gamma. Pero dito, hindi natin makukuha. So, pwede ang gawin natin is we just divide this by x. If we divide activity by x, then we should get, para makukuha natin is, notice na kung habang lumalapit ng x sa 100%, we also approach activity equal to the ideal conditions, no? Tama? So, you notice na si gamma actually approaches 1, which is the ideal. No? Tama? So, if we want to get 0.49, what we can do is we can just do, kung ganito yung given na data, no? One of the solutions, and I'll leave you it as an assignment now for the other solutions that you can come up with. Pwedeng kayo na yung maghanap ng other solutions apart from this simple solution right here. So, ang gagawin natin is we have 0.53, 0.45. So, to get 0.49, gagawin lang natin is we just interpolate, no? So we can do, since this is fairly close lang naman sila, 0.40, if you look at 0.45 and 0.53, sorry, this is 0.45 right here, itong point na to, and this is 0.53, and if you look at the this part, no, fairly linear naman siya, so we can assume na linear interpolation lang gagamitin natin. So if it's linear interpolation, then we do 0. Ang kailangan kasi natin is, wait, we need the gamma, no? So, wait. Isulat ko sa Excel. Excel natin siya. So, kailangan natin, sorry, not Excel. So, what we need is, we are interpolating 0.49. No? So, kailangan natin yung gamma at 0.49. So, we know that, we know the x, sorry. And this is 0.49. No? So, kailangan natin is x at 0.49 tayo magsulat. Ito. Okay. X at 0.49 minus, sorry. Hindi dapat ito. Wait. So, we have x at 0.49. Ito yung, sorry. Diretso lang pala. 0.49 minus, let's do one endpoint, no? We have 0. Pwede ko sigurong i-copy na lang para lipat natin to. Lipat natin siya dito. So, to do linear interpolation, ang gagawin lang natin is, so, let's do linear interpolation. So, we have 2 points kasi nandito kasi yung in between dito yung 2 values natin. Yung 0.49 kasi it's in between these 2 values, no? So, ang gagawin natin is, we do x 0.49 minus, we can do the high end or the low end. 0.49 is straight in the middle, no? So, let's just do 0.53 na lang. Or sige, pwedeng 0.45 para puro positive. So 0.45, tapos we don't know the gamma of 0.49. No? Pero we know the gamma of 0.45, which is 0.44 is equal to yung, then let's do yung ito, no? So you can do 0.45 minus, sorry. Tama. 0.53 para wala tayong negative. 0.45 divided by yung gamma ng 0.53 is 0.58 minus 0.44. So that's just a simple way to do linear interpolation, class, no? Actually, parang now that I think about it, no? Kasi the gamma is the slope, parang mas appropriate yata na ang ginawa natin is, and this is another way of doing it, no? Ang ginawa natin is, kinompute natin yung activity at 0.49. Para ang mangyayari dito is 0.53 minus 0.40, and this is 0.31, and ito. So kumbaga magko-compute tayo ng activity. Activity at 0.45 is 0.2. Tapos 0.53 minus 0.45. And activity nito is 31 and minus 0.2. Ganyan, no? So we can compute for this. Let me compute. Mabilisan lang. So, shift solve lang tayo. 0.49 minus 0.45. This is our x. Ito yung hinanap natin. Minus 0.2 is equal to 0.53 minus 0.45 divided by 0.31 minus 0.2. Let's do shift solve. This is 20. No? 0.255. So we have activity 0.255. Therefore, kung kukunin natin yung gamma, then it's just 0.255 divided by yung 0.49. Tama? So, divided by 0.49 gives us, nag-crash na naman. Pero, let's take my other calculator. 0.25 divided by 0.52. Okay? So, ito yung gamma natin. 0.52. And it makes sense, no? If you look at 0.52, it's right in between dito. 0.52. There's a gamma. So you can do that, or pwede ring if you come up with other solutions, no, apart um, from doing interpolation, pwede ring tingnan nyo yung graphical analysis, take the slope, pwede rin yun. It depends on you guys, no? Pero ito yung, I think, the easiest way to do this type of problem, no? Alright? So, yun lang siguro for today. Medyo nag-extend tayo. Apologize for the extension, no? Pero, and thank you pala, Hazel, for writing the answer, no? 0.5204. So, yun lang siguro for today. And thank you again sa mga pumasok, no? Specifically si Hazel and Joanna. So, I appreciate you guys for taking the time to come in today's session. And before I end, are there any questions? So, wala naman from Joanna. Hazel, how about you? Wala din. So, yun. Thank you guys, and I'll see you next week.
Thank you po.
Okay.
Sir.
All right.